Good evening, everybody, and welcome to the June 12th, 2025 Pacific Coast Archaeological Society General Membership Meeting. Tonight, we have Dr. Robert Dello-Russo. The title of his talk is going to be Context is Everything, Ruppia cirrhosa, and Dating the White Sands Footprints. Dr. Dello-Russo is the retired director of the Office of Contract Archaeology at the University of New Mexico. Prior to that, he was deputy director of the New Mexico Office of Archaeological Studies and the compliance archaeologist for the New Mexico Department of Game and Fish, and the owner and principal of Escondida Research Group, a private archaeological consulting firm. He has almost 40 years of archaeological experience, including field work in the Rocky Mountains, the Pacific Northwest, the Intermountain West, and the Southwest, where he served as principal investigator for dozens of funded grants and large-scale CRM projects, including at White Sands National Park. In addition, he was the principal investigator for 20 years at the Water Canyon Paleo-Indian site in West Central New Mexico. His fields of research include hunter-gatherer prehistory in Western North America, paleoclimate and paleoenvironmental studies, morphological processes, and the XRF sourcing of silicified rhyolites and dacrylites. I'm not sure if I pronounced that correctly. Dr. Dello-Russo has a PhD in anthropology archaeology from the University of New Mexico. We welcome you, and the meeting is all yours.
Thank you, Joe. I'm going to share my screen here. I think, let's see. No, that's not the one. Okay. Joe, can you see that first slide?
Yeah, it says context is everything.
Okay, terrific. Very good. Okay, good evening, everyone. Thank you for tuning into this presentation. Tonight, I'll be talking about the ages of human footprints at White Sands National Park. I and my colleague, Dr. David Rochelle, have been involved with this research since 2019. Before I begin, I'd like to thank the Pacific Coast Archaeological Society for sponsoring this monthly series. In addition, I want to say thanks to Joe Hodgelik for inviting me to participate, and to Steve Dwyer for his excellent technical assistance. As you know, my talk tonight is entitled Context is Everything, Ruppia cirrhosa and Dating the White Sands Footprints. So let's get started. This map shows the state of New Mexico and the location of White Sands National Park. As you may know, fossil tracks and trackways have been discovered at the park, and there's an ongoing controversy about the age of the human footprints. The footprints represent many of the animals that comprised what is known as the Rancho La Brea fauna, megafauna, such as giant ground sloth, mammoths, dire wolves, camelids, and perhaps saber-toothed tigers. It's estimated that White Sands holds hundreds of thousands of tracks in various states of preservation. In the first images here, we see exhumed sloth and mammoth tracks. And these are the exhumed tracks here, which are infilled imprints that were lithified and then subsequently exposed and pedestaled by the wind erosion of the softer surrounding sediments. Other mammoth tracks, not yet eroded out of the gypsum, are known as ghost tracks and are perhaps older than the pedestal tracks. This concentration of ancient prints makes White Sands a world-class fossil locality and laboratory. Also found at White Sands National Park are fossil tracks described as human footprints. As seen in these first two images, some purported human tracks are extremely ephemeral. You have one there, you have one there. This is a footprint. They're difficult to define, almost invisible. Some appear to have no toes. And based on the similarity of their sizes and gaits, the distance between the prints, it's possible that some are actually sloth prints. Others, after having been excavated, look more convincingly human, although a number are oddly misshapen. Some have 6 toes, and others, such as this one in the image here on the far right, have a big toe that almost appears to be an auxiliary appendage. While there's an ongoing debate about the contemporaneity between some human tracks and nearby mammoth and sloth tracks, what we're concerned with tonight is how the ages of the human footprints were determined. In 2021, Bennett et al. Published a paper in Science regarding their discovery of human tracks at White Sands National Park. Tonight, I'll refer to those researchers as the NPS Trackway team or the NPS team. Their discovery of seeds, right here, from the Ruppia cirrhosa plant in apparent association with human footprints led to their attempt to date the seeds. Those dates were assumed to represent the ages of the footprints. The seeds were found above, in, and below human tracks in finely laminated layers of gypsum sediments in an area designated as locality 2. And here's a profile in a trench in locality 2, and you can see the yellow line is seed layers, and there's human footprints in between the seed layers. As you may already be aware, their radiocarbon dates came back between 21,000 and 23,000 calendar years before present, or Cal years BP. These dates fall within a period known as the Last Glacial Maximum, and if accurate, would constitute an extraordinary claim, largely because those dates are very much older than the ages of any widely accepted archaeological sites in North or South America. As such, we felt that their claims and their methods were worthy of closer inspection. To paraphrase Karl Popper, the famous philosopher of science, quote, "The goal in science is not to force the data to fit a set of preconceived conclusions, but to attempt to rigorously disprove a hypothesis and determine through testing if it still holds up," unquote. The hypotheses we then decided to test were: 1, Ruppia plants grew in situ at locality 2, and 2, the LGM radiocarbon dates for the locality 2 human footprints are accurate. And please keep in mind that the controversy surrounding the dating is not meant to detract from the NPS team's discovery of the tracks at White Sands, but to subject their claims about the site context and the radiocarbon ages to the rigors of the scientific process. So let's begin with context. Here we have a geological cross-section of the Dello-Russo Basin in southern New Mexico, where White Sands National Park is located. During the Pleistocene epoch, the basin was filled with an internally drained saline lake known as Paleolake Otero. That's right here. The thick-bedded lacustrine deposits at the bottom of the lake consist primarily of gypsum, or calcium sulfate, which during wet climatic intervals eroded into the basin from the Permian age evaporitic deposits of anhydrite, such as this, now uplifted into the surrounding Sacramento, right here, and San Andreas Mountains. During intervening drier climatic times, the lake would recede, sometimes drying out completely, leaving evaporite deposits, like the selenite crystals pictured here. The final high stand of the lake occurred around the transition from the Pleistocene to the Holocene about 11,000 years ago. Following that, during the early to mid-Holocene epoch, about 10,000 to 7,000 years ago, prevailing winds swept across the dry Paleolake Otero Basin from the southwest to the northeast. And this is a satellite image of those winds blowing sediments out of the Paleolake Otero Basin into the white sands over here. Those winds eroded the exposed lake bed, transported the gypsum sediments out of the basin, and deposited them as the white sands dune field, which we all are familiar with or know about. And here's a photo of it. And over here on the downwind side of the lake bed are the white sands. The episodic winds that blow across Paleolake Otero, pictured here, easily eroded the soft gypsum sediments, created erosional landforms in the now dry lake basin known as scarps. These step-like features were initially interpreted as remnant shorelines. The oldest is the L1 erosional scarp, which formed in the late or terminal Pleistocene. It's the green lines. The more recent L2 scarp, the red lines, formed in the mid-Holocene. As you can see, each of the scarps have been mapped on both sides of the lake basin. You have two scarps on this side and two scarps on this side, the lake basin in between. In this vertically exaggerated geological cross-section of the Paleolake Otero Basin, running from southwest to northeast in the direction of the prevailing winds, we see both the L1 erosional scarp here and the L2 erosional scarp here. By way of clarification, the L2 scarp is not the same thing as locality 2 that we talked about. The human tracks and Ruppia seeds that comprise locality 2 are found at the base of the L1 scarp. This is where the NPS team conducted their excavations. There are exposed gypsum surfaces below both the L1 and L2 scarps, and they both contain numerous footprints. The Ruppia seeds are found above, below, and within human footprints. So this begs the question, how did Ruppia seeds come to be at locality 2? The NPS team asserts that they are found there because Ruppia plants grew in situ at that location in shallow fresh water. Respectfully, we disagree, and we have a different story. And here's our story. Let's first consider the ecology and physiology of the Ruppia plant. Ruppia is an aquatic plant that is most prolific in saline or brackish water. When in fresh water, it is easily outcompeted by other aquatic plants, and abrupt fluctuations between saline and freshwater environments cause it to fail. It also prefers deeper water to support its branching structure. You can see that here. And relatively clear water to enable photosynthesis while submerged. As illustrated in these images, Ruppia flowers grow in clusters on fine stems like this, like this. The stems and seeds easily detach from the plant when the water habitat becomes turbulent. This fosters the dispersal of the seeds. And in the lower right photo, we see the detached stems and seeds as they were identified at locality 2. Please note that there were only detached stems and seeds identified there, nothing else. No roots, nor any Ruppia pollen, just stems and seeds. The stems and seeds are highly buoyant. So once they have broken away from the plant, they get tangled together and they form floating mats. This photo shows an example of a large Ruppia mat at southern Owens Lake in California. You folks might be familiar with this. These mats move great distances over the surface of the lake during windy storm events. As such, we consider Ruppia to be the tumbleweed of the lake, and we believe that Ruppia mats like this formed at Paleolake Otero in the prehistoric past. Here's a schematic of the Paleolake Otero Basin at a time in the past when the lake was at a relative high stand. In this image, Ruppia plants are growing in deep lakeside embayments, and they're right here on the west side of the lake. During the summer months, across the American West, intense thunderstorms accompanied by high winds, known as seiche events, occur above inland lakes. It's likely that such events occurred at Paleolake Otero as well. The turbulence associated with these storms breaks the buoyant parts of the Ruppia plants from its lower fronds. As we saw on the previous slide, the buoyant Ruppia stems and seeds will form mats that are then transported across the lake by the winds and deposited along the opposite shoreline. These cycles of wave action then roll the stems and seeds of the Ruppia mats into balls, which we refer to as seed balls or lake balls. These materials are deposited in a strand line above the water's edge. This process, which can be observed today at many inland lakes in North America, effectively moves these plant materials from an aquatic environment into a terrestrial environment. And here you can see an example along a lakeshore of hundreds and hundreds of seed balls. This picture over here, this is not the world's largest seed ball ever found. It's actually just a close-up shot of one of the seed balls out here. So what happens when the storm ends? The winds die down, the waves recede, and the lake returns to its still water level. Seed balls are left stranded high on the shoreline, out of reach of any lapping waves. Present-day visitors to the ocean or even to Owens Lake will have noticed that the strand line can be found quite a ways back from the calm water line. It's then that humans and other creatures would walk along the shoreline, either during the present day, as seen in this image, and here's seed balls and human footprints coexisting, created in the modern day, or during prehistoric times, as seen in this image of a purported human footprint here, and partially buried Ruppia seeds and seed balls at White Sands. The track makers step on the seed balls and on the seeds and stems that derive from disaggregating seed balls, and the Ruppia seeds are pressed into the footprints, waiting, in the case of Paleolake Otero, for the archaeologist to retrieve them. Following the principle of uniformitarianism, we assume that because these seed ball events occurred today, they also occurred in the prehistoric past at Paleolake Otero. Here's some other good present-day examples of seed balls near locality 2. Some of these are disaggregating into layers of seeds and stems. These are particularly interesting photos of the same location. What's cool about them is that there are multiple layers of seeds. You have an upper layer of seed balls here, overlaying a lower layer here, which in turn is overlaying yet another layer here. Based on the preceding slides and logic, we have good evidence that Ruppia seeds arrived at locality 2 as redeposited seeds and stems in the form of seed balls. Our takeaway lesson here to address our first hypothesis is that Ruppia plants did not grow in situ at locality 2. Our second hypothesis states that radiocarbon dates for the Ruppia seeds are accurate. We contend, however, that the radiocarbon dates on the Ruppia seeds at locality 2 are too old due to the hard water effect, or HWE. Let's explore that point right now. What is the hard water effect? Water rich in dissolved ancient geologic carbon, such as calcium carbonate, is the most common reason for the hard water effect. We refer to that source of carbon as dissolved inorganic carbon, or DIC. When this ancient carbon is absorbed by aquatic plants during photosynthesis, it causes radiocarbon dates to appear to be too old. This is a well-known and well-understood phenomenon. It's also well understood that because of the hard water effect, Ruppia is too unreliable to serve as the chronological basis for radiocarbon dating. So how does the hard water effect make radiocarbon dating unreliable? Let's look again at plant ecology in the Dello-Russo Basin, this time not just for submerged plants, but for terrestrial plants as well. When terrestrial plants photosynthesize, they incorporate carbon from the atmosphere. One of the tenets of radiocarbon dating assumes that the living organism has the same proportion of radioactive carbon as the air around it. This means the plant is in equilibrium with atmospheric carbon. When the organism dies, the radioactive carbon in the plant begins to decay, and we measure the remaining amount of radioactive carbon to calculate when the organism died. Aquatic plants like Ruppia cirrhosa photosynthesize by incorporating dissolved inorganic carbon, our DIC, from within the water. Hence, their preference for submerged hard water settings. The DIC taken up by aquatic plants is ancient geological carbon that is not in equilibrium with atmospheric carbon, and this produces a radiocarbon date that is too old. With this understanding under our belts, we hypothesized that if modern Ruppia plants had been impacted by the hard water effect, we could radiocarbon date some of them and discover any age discrepancy or offset. So we sought out a modern-day Ruppia meadow in the Dello-Russo Basin. Here, once again, is a geological cross-section of the Dello-Russo Basin with Paleolake Otero at a high stand during the Pleistocene epoch. As in the case with all internally drained inland lakes in western North America, during drought periods in the prehistoric past, Paleolake Otero would recede. Happened to any Ruppia cirrhosa plants growing in the Paleolake Otero Basin at those times. It turns out that a tributary to Paleolake Otero, known as Salt Creek, right here, could retain some of its competency because it was and is spring-fed. Ruppia plants would utilize Salt Creek as a refugium to continue their existence in the basin. So my colleague Dave Rochelle went out, searched for, and found extant Ruppia meadows in the upper reaches of Salt Creek near the lava beds known as the Carrizozo Malpai. He gathered our living Ruppia samples there. In this photo, we see our sampling area, a stretch of the saline spring-fed Salt Creek. If you examine the water, you can see the submerged Ruppia plants. They're all stretched out along here. This location exhibits a number of the habitat attributes for Ruppia cirrhosa, including low energy, stable sediment deposition, high levels of light, and the presence of consistent but not fluctuating saline water. As the push probe shows, the sediment in this Ruppia meadow is gleyed and massive, not characterized by the thinly laminated strata that are seen in the trackway horizons of locality 2, as you might recall. As an additional side note, we found that Ruppia roots and pollen are both found in the present-day meadow as well. And here's a photomicrograph of Ruppia pollen. Remember, neither the roots nor the pollen are found at locality 2. So our takeaway lesson there, once again, addressing our first hypothesis, is that Ruppia plants did not grow in situ at locality 2. So as we were beginning our study in Salt Creek, several colleagues, Jack Oviatt, Dave Matson, Dave Rohde, and Lauren Davis, searched the herbarium at the University of New Mexico. There they found specimens of both Ruppia and bulrush, that had been collected in 1947 from the Malpai Spring, pictured here on the southwest edge of the Carrizozo Malpai. When Oviatt and Associates radiocarbon dated the Malpai Springs Ruppia specimen, which is pictured here, it returned an age of 7,400 calendar years BP. As a quick aside here, I would like to make an important point about radiocarbon dating. When radiocarbon scientists refer to years before present, years BP, the standard reference point for the present is the year 1950. So 1947, the year the Malpai Spring, Ruppia, and Bulrush were collected, is essentially the present in radiocarbon dating. The difference between this modern aquatic plant's radiocarbon age and its expected modern age is called the age offset. So this very large age offset, 7,400 years, helped us to verify that a hard water effect does exist in the waters of the Dello-Russo Basin, and that the hard water effect causes radiocarbon ages to be too old. If this Ruppia had been a modern terrestrial plant not subjected to the hard water effect, it would have returned a modern age. Of additional interest is the second discovery by Oviatt et al. Of the 1947 Malpai spring bulrush specimen right here, a plant that lives in a partially submerged habitat and which we refer to as emergent vegetation. It produced a radiocarbon age offset of only 389 cal years BP. This finding illustrates an important point to which we will return later. So with this information in hand, we proceeded in the spring to collect living Ruppia samples from the Salt Creek study area and then radiocarbon date them. Interestingly, we found that the modern Ruppia plants right here on this rake, and all from the same meadow, returned 4 different radiocarbon ages. In addition, and perhaps more importantly, we found that these 4 ages spanned a range of 1,000 years. This suggests that the Ruppia plants were impacted differentially by the hard water effect. And the reason for this temporal variability of the hard water effect in a single Ruppia meadow, we speculated, could be because 1, the dissolved inorganic carbon is unevenly distributed throughout the water in which the Ruppia grows. Hard water variations in plants collected in the same season supported this idea. And or 2, Ruppia plants take up DIC at different rates during different seasons of growth. We collected additional Ruppia plants during the fall, and this also proved to be true. So we now knew that individual meadows of Ruppia could exhibit a range of radiocarbon dates. What about Ruppia seed balls? To investigate the potential variability in a single Ruppia seed ball, we devised an experiment. We recovered a Ruppia seed ball, this one, from the same stratum as the trackway layer at locality 2 and divided it into 3 sections. We then pulled 2 Ruppia seed samples from each seed ball section and radiocarbon dated each of those 6 seed samples. A previously reported radiocarbon age for Ruppia plant fragments from locality 2 here came to 21,687 cal years BP. Would the radiocarbon dates from our Ruppia seed ball compare favorably to this? Of our results seen in this table on the slide, 2 samples in the green, 12,962 and 21,708, were rejected because their errors were too large, well over 1,000, plus or minus 1,000, and their sample sizes were too small. However, 4 of the 6 samples in the red were accepted. The 4 accepted dates fell between 20,834 and 22,411. The average of all 4 accepted dates is 21,738, which is very similar to the previously reported date from locality 2 of 21,687. So you have 21,738, 21,687. In fact, two of the dates from the seed ball are basically identical to that locality 2 date. More importantly, however, these samples from a single seed ball provide a 1,577-year range of calibrated years. Because these dated samples came from the same seed ball, we suggest that it simply means that the Ruppia plants were differentially impacted by the hard water effect. So now we've seen age variability within living stands of Ruppia at about 1,000 years and within a single Ruppia seed ball around 1,600 years. With that information in mind, let's revisit the dated stratigraphic profile published in Science by Bennett et al. In 2021, which is this. Based on the dated Ruppia trackway horizons 1 through 7, which are here, 1, 2, 3, they're called TH, trackway horizons. The NPS trackway team concluded that the profile from bottom to top represents almost 2,000 years of human occupation in the Paleolake Otero Basin. But does it? Let's look more closely. Ruppia seed dates from trackway horizon 6 alone, right here, just this one, spanned 1,000 years from 21,100 to 22,100 cal years BP. As we saw in our discussion about the variability of the hard water effect, that range of dates could have been produced by just a few Ruppia plants from a single meadow during a single growing season. The purported 2,000-year human occupation of the Paleolake Otero Basin could simply represent the production of Ruppia plants over the course of 1 to 2 years. Another interpretation of that span for the 7 trackway horizons at locality 2 could be that it represents a series of summertime storm events over a period of 7 years, where each new layer of seeds represents the strand line from that year's storms. So in that scenario, prehistoric humans would have walked across the shoreline of Paleolake Otero over the course of 7 different years, not 2,000 years. As some of you might recall, the NPS team in their 2021 paper sought to support their chronological claims by asserting that their reported Ruppia dates at locality 2 were in perfect stratigraphic order, that is, oldest at the bottom and youngest at the top, with no inversions. At first glance, that appears to be the case. But to test that claim, there's an important aspect of their methodology that must be examined. For each reported date, the NPS team included the number of seeds in each dated sample. That's over here. These are referred to as aliquots. The aliquot sizes, the aliquot sizes range from, well, they're listed right here. And they range from 40 seeds in some aliquots to as many as 80 seeds in others. The NPS team provided no explanation for such uneven sampling. It's important to stress here that each individual seed in a given aliquot, let alone 40 to 80, but each individual seed in a given aliquot had the potential to return a unique hard water affected radiocarbon age. In addition, keep in mind that each reported age for each aliquot is an average of between 40 and 80 individual seed ages. So each aliquot age could easily have spanned 1,000 years or more. And any chronometric variations or inversions that actually existed in a given trackway horizon could have been smoothed out by the averaging of those large size aliquots. This means that the argument for stratigraphic integrity by the NPS team is questionable at best. So given all those sources of variability in the locality 2 radiocarbon chronology, is there a way to adjust the Ruppia dates for the hard water effect? Let's first look at a geochemical expression known as delta 13C, right here. Delta 13C values are measurements of the ratio between the stable carbon isotopes carbon 13 and carbon 12 in a given sample, and they're expressed as parts per thousand or parts per mil. These values are often reported with radiocarbon dates. Now let's look at plant photosynthesis. Here we have mesquite, which is a C3 terrestrial plant, where the C3 classification denotes a type of photosynthetic pathway. Bulrush, as we've seen earlier, is an emergent C3 plant, and Ruppia is a submerged aquatic C3 plant. So each one of these plants has the same photosynthetic pathway, but they have really different habitats. So a terrestrial plant absorbs carbon from the atmosphere, has a very low delta 13C value of minus 30 parts per mil, and when radiocarbon dated, returns a modern age, which is 0. In comparison, the emergent bulrush absorbs carbon from both the atmosphere and from DIC in the water. Its delta 13C value at minus 23.9 parts per mil is higher than mesquite, and it has a radiocarbon age offset of around 389 cal-years BP. Finally, the aquatic Ruppia takes all of its carbon from DIC in its hard water habitat, produces an even higher delta 13C value of minus 13.6, and returns a radiocarbon age offset of around 7,400 cal-years BP. So as we see from the preceding graphics, elevated concentrations of DIC during photosynthesis can lead to relatively high delta 13C values for Ruppia relative to plants growing above ground or to partially submerged plants. Thus, the variable assimilation of DIC not only affects delta 13C values, but also affects the radiocarbon age offsets of the plant. To counter our argument about the age offsets, the NPS trackway team insisted, again, that Ruppia grew in situ at locality 2, in a shallow freshwater habitat where the hard water effect would have been lower or non-existent. If Ruppia had grown in situ at locality 2 in a shallow water or emergent setting, the delta 13C values of the dated samples would reflect that. Unfortunately, the NPS team has not yet published these values, despite numerous requests. We have already made several arguments against the NPS position, and we have underscored the relationship between delta 13C values and radiocarbon age offsets in peer-reviewed publications. We maintain that Ruppia grew in single-species meadows in relatively deep, high salinity, hard water-affected environments, and that it was deposited in strand lines on the Paleolake Otero shoreline via seed balls. To put this another way, when the NPS team argues for a shallow freshwater habitat for Ruppia at locality 2, they are asserting that those plants grew in a Ruppia habitat that is not observed in any contemporary ecosystem. There is no present-day analog for their version of Ruppia ecology anywhere in the world. So we've identified a relationship between delta 13C values and radiocarbon age offsets that applies to modern terrestrial, emergent, and submerged aquatic C3 plants. Modern C3 plant samples with enriched delta 13C values, those that are higher or less negative and closer to 0, exhibit larger age discrepancies in their radiocarbon dating. In this slide here, we plotted this relationship for the modern C3 plants graphically, with blue being the submerged Ruppia, yellow being the emergent bulrush, and green being the terrestrial mesquite. The relationship between delta 13C values and radiocarbon age offsets is strong and positive, as evidenced by our R-squared value of 0.83. For these modern cases, the age discrepancies are the differences between the radiocarbon age of the sample and the known and expected modern age, which would be 0. For prehistoric samples, we do not know the actual age of any of these samples, only their hard water affected radiocarbon ages and their respective delta 13C values. So we collected 17 prehistoric Ruppia seeds from the same strata as those from trackway horizons in locality 2. We then radiocarbon dated them and plotted their respective delta 13C values on our graph, the red dots on the sloping line. As you can see, all except one of the Ruppia seeds had relatively high delta 13C values between about -11 and -4.5 parts per mil. When plotted, they translate to age offsets between 6,200 and 8,800 cal years BP. So what do the results of our research mean in terms of the peopling of the Americas? Let's see if I can get this slide to advance. There we go. Here on this map, we see the so-called and no doubt familiar ice-free corridor or deglaciation corridor. It's the northern part of the red route. And the Kelp Highway in blue. Both are purported routes of entry for the first Americans. As I noted previously, the most widely accepted dates for the earliest archaeological sites in the Western Hemisphere fall between 14,200 and 16,000 calendar years ago. Genetic studies suggest around 16,000 calendar years ago for the initial colonization in the New World. Looking again at the assertions made by the NPS team for the ages of the human tracks at locality 2, recall that they claimed a 21,000 to 23,000 cal year BP range of ages for them, based on the radiocarbon dates of Ruppia seeds. It's an extraordinary claim that the NPS team characterizes as, quote, paradigm changing, because if true, those dates would push back the presence of humans in North America by at least 7,000 to 9,000 years into the last glacial maximum. As I outlined in this presentation tonight, our research demonstrates that context is everything, and that the chronological studies using Ruppia seeds must take into account both the well-known hard water effect and details of Ruppia ecology. We have also developed a useful relationship between delta 13C values and calibrated age offsets. As demonstrated by that relationship, we have argued that the Ruppia dates at locality 2 could have offsets between 6,200 and 8,800 calibrated years. By applying these offsets, we derive corrected ages for the Ruppia dated tracks between 16,800 and 12,200 cal years BP. These corrected ages fall in line with the most widely accepted range of earliest ages for archaeological sites in the New World, and they also conform with the timing of human entry into North America, estimated by genetic studies. So it's our firm belief that the footprints are more likely to be Folsom, Clovis, or maybe even pre-Clovis in age. This is still a noteworthy find, but we don't agree that the ages of the White Sands footprints are really a paradigm-changing discovery for the archaeology of North America. The exact age of the human footprints at locality 2 has become, for some researchers, a focal point in discussing when and how humans colonized the Americas. As such, and in following Popper's admonition about the goals of science, we have critically examined the context and the Ruppia dating at locality 2 and demonstrate that there remain important issues pertaining to the geological context of the Ruppia seed layers. and site formation processes at the site, the ecological requirements and physiology of Ruppia, and whether the Ruppia seeds could have been subjected to the hard water effect. As a result, we argue that the claim of a last glacial maximum age for the human tracks at locality 2 is misleading and erroneous. And with that, I conclude my presentation. Thank you very much. And I'll be happy to answer any questions if people have them.
I have a question, not so much a scientific one, but when one of the first slides you showed where the footprint was pushing down on one of those Ruppia balls
Yeah,
and embedded within the footprint, do you think they were are they walking on these Ruppia balls because it was softer on their feet, or are these Ruppia balls hard and brittle and tough on their feet, or were they looking for food? Why do you think they were walking where the Ruppia balls were?
that's a really good question, Joe. Uh, the Ruppia balls are just washed up on the shoreline. I mean, it's no different, I suppose, than people today walking along the ocean shoreline, and there's all kinds of wrack washed up there, shells and wood and debris, and people walk through that. Why they were doing it, I don't know. I'm assuming they were either going from one place to the other or were just playing in the water. There were small possible child footprints there. So that's a good question. I'm not sure I can actually answer that, though.
Are the Ruppia seeds edible?
Not that I've ever read, but that's actually an interesting question. Perhaps they could be parched and ground up for something. That you're the first person I've actually heard even ask that question. That's a good one. Somebody should try it.
Does anybody else have any question? That's not so hard.
Yes, I do. Do you have any theories on the 6 toes?
Oh, that photo. Yeah. Yeah, that was really bizarre. I'm not really sure what that was. Let's see.
These are
This photo
footprints
right-
from bare feet. It looks like, to me, I thought when I first saw it, well, maybe if this is a really, really soft or a yucky surface or something, they might have some kind of a sandal, if only, in the picture on the right there, it looks like the upper part of the foot from the middle more or less to the toes is a little more pronounced than the heel is. When you walk on wet sand and such, there's a tendency, at least with me, to put my weight on the ball of my foot toward the front. Could they have had some kind of a sandal, kind of analogous to a snowshoe or something that they would wear in this environment to protect their feet or to prevent their feet from digging into the ground? Or how many 6-toe prints were there? Was it just a couple or several?
Oh, there's several. And I'm not sure what that is. The original, when the footprints were first discovered, uh, very few, if any of them, actually exhibited any toes at all. They looked more like something like this. They were toeless. It wasn't until later that the excavators started having toes with them. This particular one, I'm not sure what it is. It occurred to me that this might be one foot superimposed on another footprint, perhaps, but I'm really not sure. There is a condition that some people have in the world where they have more than 5 toes. So, so I suppose it's even possible that that condition was exhibited by some of the people down there.
I had a cat like that one time, had 6 toes, which I understand is not way, way, way uncommon. I don't know about in human beings, but so they would apparently, these are bare feet on the sand. They wouldn't be trying to, are there any other seeds, thistles, or whatever those little plants are that puncture your tires on your bicycle when you're a kid that I hate? I have some
Goat head.
growing across the
Yeah,
street from me.
the goat
Would
head.
there be something else there besides what you're showing with the seeds that you studied? Would there be something there that you might need to protect your feet from?
No, actually, there's no indication that any of these people were wearing sandals that I've seen. And also, there are no other plants in these deposits, which is really curious. You're talking about like goat heads or something like that that you would
Yeah, right.
step on. Yeah. Interestingly, if there had been other materials to date, that especially if they were terrestrial or even emergent plant remains, I think the researchers would have tried to date them. But this is all that they found are Ruppia seeds and stems. And some later on they found pollen, but no Ruppia pollen. So that's really all that they have, I think.
Could that six toe be an impression of maybe a walking stick that they were carrying?
That's an interesting thought. It's possible. Um, we don't know exactly why these people were out there walking. There's been any number of artists' conceptions of what's happening out there, and it's possible that someone could have had a walking stick, certainly.
Any good guesses what they're doing out there? Hunting waterfowl or looking for arrowheads, or some particular reason they easy to walk through that area because the ground was soft? Any ideas why they were there to begin with?
No, I don't know. Your guess is as good as mine. There is some claims that they were out there hunting sloth and mammoths, but we have no archaeological remains to support those suggestions. There's one claim that some people were out there trying to hunt this one sloth, and apparently the tracks of the sloth and the tracks of the humans were such that they created this story about that. But there's some serious issues about the contemporaneity of all these tracks and how that's determined.
What is the nature of the ground away from the area on the lake? Is it angular, hard rock that you would not want to walk on if you could avoid it, or what's the surrounding terrain like?
Well, to the downwind side, to the east side, it's the White Sands sand dunes, and that's all gypsum sand, just like the gypsum sediments that this person was walking on. Um, Beyond it to the west, there's some more rocky, harder sediment. It's not lake bed. It's more of a desert environment there. Whether it was a desert environment then is not, probably not the case, but um, I think, it's possible that the people were walking barefoot because they were at the beach. They were on the shoreline. It was wet, it was soft. They didn't necessarily have to walk in other places with
Maybe it just
bare
felt
feet.
good.
Yeah, it could have. We certainly have evidence in Western North America for sandals that are, close to 10 or 11,000 years old. There's some in Oregon that are really old. So it's logical to assume that they probably had some sandals.
Well,
Just
that was one of my first impressions, is like, why are they walking barefoot? I like the idea, it just felt good.
Yeah, imagine this is just wet, soft sand that you're walking in. Lots of people take their shoes off when they get to the beach just to do that, walk in the soft, wet sand. So
Yeah, I certainly do. Anyway, very interesting stuff.
thank you. Any other
Um,
questions?
yeah, I thought that they dated some ponderosa pollen to roughly the same age, and that also that there's some OSL dates for quartz crystals from similar event horizons. And all of those dates tended to coalesce around 20,000 years ago or something. Do you know anything about those?
Yeah, I do. Let me talk a little bit about them. I'm not a specialist in OSL dating, but I collaborated with the other folks I mentioned, Dave Madsen and David Rohde and Lauren Davis, and on an article in Paleo America talking about these very issues. The pollen, there's some really controversial things that the NPS research team did in their pollen processing, their approaches to flow cytometry and their sieve sorting. They sorted out, they biased it towards large conifer grains that were larger than 70 microns. And it's likely that a lot of those large conifer pollen could have been reworked from older deposits. There were no small grain size pollen shown in any of their figures, like Artemisia, like sagebrush. And that purportedly made up 34% of their samples, with pine only being 5%. So where are the Artemisia grains that would have possibly dated much younger? The radiocarbon ages of pollen and Ruppia, if you look at them closely, they appear to be consistent only because the error bars for the pollen are so large. They span half the Holocene. That's like 5 or 5,500 years. So the dates overlap. So they're really not consistent in that sense. This is what I think of that. The dating of the tracks using Ruppia on the one hand, pollen on the other, and OSL on the other is like a three-legged stool. When one leg is shown to be broken, like we think the Ruppia dates are not accurate, then the reliability of the OSL and the pollen dates hinges on the accuracy of those Ruppia dates. And if they're not accurate, then these probably are suspect as well. And as for the OSL, that's a little bit more technical, but the OSL samples, among the things that we had problems with was the sample elevations for the OSL samples were never reported. So we don't know how they actually measured the elevations at the site. Did they use a total station? Did they use tape measures? They also failed to demonstrate the purity of those quartz samples that you talked about. There's no good argument for the source of quartz crystals during the last glacial maximum. We don't even know if the dunes existed back then. There's also a debate about whether those quartz crystals were partially bleached. If they were bleached, then that resets the clock in the OSL dating scheme. And we also don't know the water content of the OSL samples. They did a poor job of reporting that, and thus any calculated age estimate may be incorrect. The NPS team assumes, but they don't demonstrate, that the water content of the dated OSL samples were near saturation for the entirety of the last 22,000 years. And that sort of is a mind-blowing thing for us to be expected to believe. The other thing about the OSL samples, and I want to point this out, this profile that you see here, this is an image that they published of their profile. Keep in mind that they didn't tell us this until much later, but this is an assembled photo mosaic. This is not one picture. And those photo mosaics, when they're stitched together, they produce dimensionally distorted images. This has a serious implication for the validity of their stratigraphy and their claims of associative context. The upshot of this is that the OSL samples were not taken between trackways 1 and 2. If you look at this profile, you see here on the right, TH1, trackway horizon 1, trackway horizon 2. They claim that if you extend these little surfaces, these dotted lines are the trackway surfaces, if you extend them across, trackway 1 goes under the OSL samples. You extend these lines across for trackway 2, it goes just above the OSL samples. they're arguing that those samples were taken between the trackway horizons. And that's patently bogus. They were taken from a different stratigraphic unit. If you look at the sediment here, this is a brown or tan sediment right here, and it interfingers with this darker blue-gray sediment in which the OSL samples are found. These were laid down at different times, so they are not in between trackway horizons 1 and 2. So the fact that they supposedly support the Ruppia ages that are artificially old is just an artifact of their bad methodology, I think. So hopefully that helps you understand that. That's the best I can give you.
Well, yeah, and thanks for the OSL update. It is interesting that the material has a totally different color there. But I
Yeah,
don't understand the three-legged stool hypothesis. Why? I mean, so sure, the Ruppia dates, just toss them out. But then, you know, the pollen dates might still have some validity. And I don't know, I live in a ponderosa forest, and there's this huge signal. I mean, ponderosas just dump this amazing amount of pollen every day.
Yeah.
You know, and, you know, I could look at the pollen on the windshield of my truck and say, oh, well, you know, maybe that's fossilized pollen from 1,000 or 20 or 10,000 years before that just blew onto it. But it seems more likely that it just blew onto it that day. So if you had a pollen that was landed in a footprint and you sampled that pollen, I would think that would be pretty contemporaneous with the footprint.
Yeah, well, you're equating the two processes, the wind-driven pollen and the shorelines that are impacted by waves and torn apart and redeposited and torn apart and redeposited by wave action. They're really different processes. And the likelihood of older pollen deposits being mixed in with pollen that's laid down that day is very, very high. And they don't really address that. They don't really talk about the mixing that goes on in those sediments right there at the shoreline. And that's one of the things that we had problems with even with the Ruppia. It's like we don't know if some of the Ruppia that's there was from older deposits and was mixed in when the shoreline got chewed up by wave action or not. It's a really dynamic environment. It's not this sort of passive environment like your windshield might be. So you want to consider that for sure.
But if it's all that dynamic, wouldn't it tear up all the footprints as well?
It could, but we don't know what went on between when the footprints were laid down. And I don't even know exactly where the pollen was recovered from, but don't forget, these are tiny little grains. They can be moved around a lot. And I guess, according to David Rohde, the larger pollen grains like ponderosa pine have a greater tendency to be redeposited than the smaller grains. And that's something, it might be worth, if you're really serious about this, looking at our article in the Paleo America Journal, because Dave talks at length about this problem.
I did. I read your article and I liked it, but I still have these questions.
Well, that's what I can tell you right now. We think they haven't really successfully addressed the issue of redeposition of older grains of pollen.
Just
We have some serious problems with the OSL that I just outlined, and the Ruppia dates are, upwards of 9,000 years too old. So how are those? And also the pollen ages. If you look at the radiocarbon dates for the pollen, this is what I said before, they have errors of 5,000 years, plus or minus 5,000 years.
Yeah.
That's huge.
Yeah.
You know, it's half the Holocene. I guess if it was half the Holocene, it would be plus or minus 2,500 for half the Holocene. Anyway, it's huge. And because of that, when they lay those error bars over the radiocarbon dates, wow, lo and behold, they overlap. I mean, that's like saying that something that happened at Mesa Verde in AD 1200 overlaps with pollen that could be 10,000 years old, and that therefore they're the same age. And clearly that's not the case. So you have to really look at those error bars on the pollen and ask, why are the errors so large?
Yeah,
Yeah.
I hope that helps.
it does. But it just makes me ask more questions.
Well, that's good. That's a good sign. You're on the right groove there for sure, because I think there are more questions than there are answers out here about what's going on. We don't really know what dates to think are correct. You know, I don't think the OSL dates are correct. I don't think the Ruppia dates are correct. The pollen, they have to go back and redo that. And there are people going out there right now to try to recreate some of this and redate some of this. So hopefully this will get sorted out. I mean, that's the whole idea of science, right? Is to test these claims. If they're right, somebody should be able to go back there and reproduce what they've done. But so far, I'm as big a skeptic about this as any people. So asking lots of questions is a healthy position to be in.
Dr. Dello-Russo, there are some
Yes.
questions in chat.
Okay. Can you read
A
them
good
to
one
me?
that Jim Lamott asks about the possibility of ever visiting the trackways. Will they ever be open to the public?
No, you can't find it.
Oh, that's a really good question. Right now, I'd say no. They're on, what's interesting about that location is that it's part on the White Sands National Park, where the White Sands researchers did their study, and it's part on the White Sands Missile Range, which is highly controlled, and almost nobody gets to go out there. Some researchers do, but the general public, until they come up with a way to protect those deposits out there, I'm not sure that the national park is willing at this point to allow the general public out there.
No.
Lots of people have asked about it though, and understandably.
Can I ask you a question about the pollen? So I'm not an archaeologist. I'm a biologist by training, but we've got 5,000, 10,000-year-old pollen flying around now. I mean,
Well,
that stuff is that tough?
It is that tough. It's an amazing thing. It has a cuticle on the outside of the pollen grain that's called pollenin, I think. And it's really, really durable. I mean, amazingly so that you can find a pollen just doesn't get destroyed unless it's in a really acidic or alkaline environment, you know. So yeah, the preservation of pollen is one of the great reasons why we're able to reconstruct environments going back through time, because pollen does preserve so well.
Wow.
Yeah, it's pretty amazing.
There's a question for you. One of your early slides, I believe it showed 4 layers of seeds with a fairly substantial non-seed layer in between each.
4 layers of seeds. Oh, okay.
Yellow dotted lines.
That's this one, I think. Let's see. This image right here. Is that the one?
That's the one. You can't really tell how thick those, I'll call it non-seed layers are, but what's happening with the climate there that seeds only accumulate and then must be many, many years of non-seeds, and then there's a seed layer, and then more years of non-seeds?
Well, first of all, keep in mind that this may just represent, this profile that you're looking at here may just represent a few years. It doesn't necessarily represent many, many, many years. We just don't know because the dates are not accurate and there's so much age variability in these Ruppia deposits. So each one of these layers has a 1,000-year range of dates in it, and they all basically overlap. So it's possible that, like I said before, these could represent strand lines that are formed when you have a storm event that washes the seeds into this location. Now, the fact that it didn't happen in here may be that it's just one of those a year or a period of time when there weren't that many storm events. I don't know. Keep in mind too that the footprints are also right in the seed layers. This graphic is kind of misleading because it seems to suggest the footprints are well between the seed layers, but I think they're actually supposed to be right on top of the seed layers. So I'm not sure I answered your question.
Yeah, not sure there is an answer, but yes. And then you kind of touched on it.
Okay.
Where
Yeah, it's
else?
a good question. I mean, go ahead. What?
I was going to say, and you kind of touched on it. Is there anywhere else in the American West that would have a similar geology that you can use as a comparison to this? I mean, there's lots of dry lake beds. There's lots of high wind. There's lots of sand dunes.
Actually, down in the Guadalupe National Park in Texas, which is actually not far from White Sands as the crow flies. It's way, way over in the extreme eastern part of Texas, or I mean, western part of Texas. There's gypsum sand dunes there as well, and a lake, a Pleistocene lake there as well. I think they've gone over there and started looking around there for similar discoveries. So yeah, there are some others. There's some of the other inland lakes like Bonneville Lake, Great Salt Lake, and Owens Lake, and all these other lakes in the Great Basin. They're all similar. They're just not, they don't have the gypsum geology that White Sands or Guadalupe Mountain National Park has. But it's a good question. They should start looking. And I think Bennett, who was the lead author on that original paper, he's a footprint specialist, and I think he's been trying to expand his horizons and look in other places.
Did we finish the questions in the chat?
One more question. I'll be brief. I don't understand the significance of the water content in the OSL layers. Can you help me a little on that?
Wow, and getting out of my bailiwick here. No, I'm not really sure exactly why. I think what they were saying was that the water content in their samples, it does affect how the processing of the OSL sample proceeds. And I think they were arguing that the water content was constant over 22,000 years, which seems a little hard to believe because the climate wasn't constant. So I don't think that the water content in those particular sediments would necessarily just be static over all that time. Why that's important to know in OSL dating, I apologize, but that's just not my forte. That is covered pretty well by Christina Neudorf in that Paleo America article. If you read that, she's really explicit about all the issues that she found with the OSL dating. So I would direct you to go back to that article and look again at that.
Can someone post a link for that article, please?
Post the length of it.
Yeah, chat in the chat. Or
The
Actually-
link, not length, link.
the length of it. Yeah, I don't know. Let's see.
Oh, Link,
Link.
Link.
HGB.
Okay, let's see. 1, 2, 3, 4. This fourth article here is called Unresolved Persistent Problems with the White Sands Locality 2 Geochronology. And it's in Paleoamerica, and it was 2024.
Good.
Okay. Thank you very much. I'll put my picture back on here. Dr. Dello-Russo, I'm going to be giving you a certificate of appreciation for tonight's talk. It's frameable. You can hang it right in your best spot on the wall. And I wanted to let everybody know that there are no meetings until September. In September's speaker is going to be Dr. Douglas Kennett. And the title of his talk is Maize Domestication and Dispersal in the Americas. It's going to be an in-person and Zoom meeting. And hopefully everybody will have a good summer and come back. Again, I want to thank you very much, Dr. Dello-Russo, for your
Well, you're
enlightening
welcome,
talk.
Joe. You're welcome. Can I make one more point here before we go? I was thinking that somebody would ask this question about what other kinds of archaeology are found around these trackways at White Sands. Have there been any other sites found around White Sands in that whole park that could be the same age as these other sites? And what I wanted to say about that was this picture here. This is a picture of the White Sands, the Dello-Russo Basin. Here's the Paleolake Otero. To the east of it is the gypsum sand dunes area, White Sands. All of these dots are Paleo-Indian sites that have been found in and around the Dello-Russo Basin. The dark red ones are Clovis. There's 5 or 6 of them. There's a Clovis Folsom site. All the rest, the pink ones, are Folsom sites. Archaeological work has been ongoing in the Dello-Russo Basin for well over 50 years. In that time, they have surveyed over 1 million acres, and over 50,000 square meters have been excavated. 3,000 radiocarbon dates have been produced, and of those, 2,600 are dated hearths. This work has been done across every landform in the entire region, and nothing older than 13,000 years has ever been clearly identified.
Wow.
So keep that in mind. This thing is a real anomaly, these footprint dates. And also, people wanted to know if there have been any artifacts found with the footprints. And yes, there have been lithic artifacts found in the Paleolake Otero Basin, also known as the Alkali Flats. But so far, they've only been found in surface contexts, and most archaeologists consider them to be non-diagnostic flakes, irregular cores, and angular debris. Although there are a few archaic period projectile points that have been found. Most recently, some controlled test excavations in the Alkali Flats uncovered an early archaic Bajada-style projectile point, which dates at most 8,000 years old. There are 2 examples, 2 sites in the sand dunes, one right outside of Paleolake Otero and another over by Holloman Air Force Base, which is just to the east, where they have found structures in the sand dunes that date to around 9,000 years old. These are some of the oldest sites, and this is basically what the archaeology out there looks like. There have been no other evidence of anybody older than 13,000 years out there, so you can get some perspective on this. So that's what I had to say, Joe. Thank you. That was Just a point. I thought somebody would ask that question.
I should have asked that. I was interested in that. Thank you. Okay, well, again, wanted to thank you. Thank you, everybody, for joining us tonight. We'll see you back in September. And everybody, please have a good evening and a nice summer. Good night.
Okay, thank you. Good night.
Thank you, everybody. And Dr. Dello-Russo, very good talk. Thank you very much.
Thanks, Stephen. I appreciate your help.
Good job.
All right, talk to you again soon.
Thank you.
Bye-bye.